So I'm gonna make a new project. Save it. Call this E511 or not Ansys, RMxprt example. And if you go to Maxwell,
Alex, if you want, you can bring it.
Oh.
Or you
Yeah, maybe a little higher. So yeah, that's good. Oh. Alright, so you have a new project. If you go to Maxwell, there's a tab that says RMxprt, this tab at the bottom, and the Maxwell model wizard is what you want to select, and once you finish, it'll create a Maxwell design for you basically, and they have a lot of different types of machines. So for this one, I'm just going to do an IPM motor, but they have induction machines, synchronous machines, and commutating machines. So IPM synchronous machine is what I'm going to just do as an example right now. And there'll be these different parameters. So for the stator and the rotor, you'll have to input different dimensions for the design. So right now I'm just going to choose a bunch of arbitrary numbers just to show that it'll generate a motor basically. But if you have your own design in mind, you can obviously input the numbers you have. You could sketch this on paper and say I want the outside diameter of the stator to be this width, and I want the inner diameter to be this width, and I want the rotor to be this diameter as well. And then you can go ahead and import all this to this RMxprt design. So first, the machine should already be selected. So I'm going to double click on Stator, and I'm just going to do a 4-pole 36 slot IPM motor, and the circuit type should be fine. There's different circuit types if you want it to generate a circuit along with the design, but just a Y configuration is typical, I guess. And then you can choose the type of slot that the stator will have. So I'm going to choose this rectangular slot, and I'm not going to click position control, apply, and then I'm going to go into core, and I'm basically just choosing arbitrary values for this. So it'll show you a sort of cookie cutter of what it'll look like after this. So I'm just going to say 250 millimeters outer diameter, 181 for the inner diameter. I'm going to make it 200 millimeters long, and the stacking factor I think is the lamination stack. It's like the ratio of iron to air in the laminations. So I'm just going to leave it as default. And then the steel type, I'm going to import the Nippon steel that's on canvas. So, whoops. And that's all we need to do. Apply. So that's basically the cookie cutter thing I was saying. That's basically the outer diameter and the inner diameter of the stator. And then the slot. So you can have it just choose values for you, but these values basically correspond to this. I don't think I can zoom in on it. It's kind of annoying, but I'll try to show you. So there's these different lengths here that show you what you're actually inputting. So I'm gonna unclick auto design and hit OK, and then it'll let me put values in. So I'm just going to choose basically random values for this. So HS0 and HS1 are like this pole face dimension. I'm just going to make those 2 millimeters each. And then HS2 is the depth of the slot. So I'm going to make that, I don't know, 15 millimeters, I guess. And let's see. Whoops. And for BS1 and BS2, I might need to do some like math, because if you make it too wide, there basically won't be like a slot tooth. So maybe for now, since I don't want to do that math, I'll just let it do an auto design, so that it makes sure that there's like, instead of like setting this distance to like 20, but there not actually being enough space for a diameter of like 181, then I don't know if you can really see that, but I'm just gonna let it do auto design so that it doesn't like give me an error. I mean, maybe I'll input the value and then see if it gives me an error, and then I can change it and show you that you can just go back and change it. So yeah, I'll just write like, I don't know, 10 for this millimeters and BS2, or I'll do like 11 here and 11 here and 10 here. And then hit apply. Okay. And then winding. I'm just going to do one winding layer. I'm just going to hit OK for now. And then this shows you basically what the winding configuration is going to look like. So from this, since it's 4 poles, this will be basically facing out, and this is current facing in, this is current facing out, this is current facing in. So if this is facing out and this is facing in, there's basically field lines pointing this way, and then here there's field lines pointing this way, and then pointing this way, and then pointing this way again.
Okay, so Alex, please, just something to explain. Alex said this machine is RPM, permanent magnet, but you don't see magnets. Why? Because internal magnets are available.
Yeah.
That's why you don't see that. Number two, he said the machine is 4 poles, but here we have how many of these slots? 36, Alex. How many slots do we have?
36.
36. So 36 divided by 4 is 9. So every 9 slot is for one phase. Every 9 slots is for one phase. And because I have more than 2 slots, I have 9, I can do sinusoidal coil distribution. So this has the luxury that I can put sinusoidal. So my flux doesn't look like a wall, it looks like a sine. So the torque would be smoother. Okay, just wanted to add. Okay, go ahead.
Yeah, basically what I was trying to say is these slots are facing out and these slots are facing in. So then if you can imagine the 3-phase, if you have this phase A, when it's at the peak value, there'll basically be field lines like this. And that would attract the 4 poles from the motor. All right. So I'm going to say parallel branches is going to be 1. So if it was 2, it would basically be like, the circuit would be like this. And there would be like a parallel one. And some motors have parallel branches, but I'm just going to say there's one parallel branch for this. And number of conductors, I'm just going to say 60, basically just arbitrary for now. And number of strands is basically like the number of conductors per conductor. So I'm just going to say 1. And wire wrap, you don't really need to do this. I'm just going to use 0. And the wire size, I'm going to leave it as 0 for the auto design also. And then the conductor type, I'm going to change it to copper. Okay. And yeah. Yeah. Basically strands is like it would be basically like adding parallel paths, but I don't think it would necessarily give you an advantage. It would probably just change. If you increase the number of strands, you would decrease the maximum current density you could have. Because, well, actually, no. That's in terms of parallel branches. Sorry. In terms of parallel branches, if you start increasing the number of parallel branches, you can only fit so many wires in here, right? So then if you have like 4 parallel branches, then you'll be able to, these are all basically in parallel, so then the current going into the node where they all connect is basically just going to get distributed evenly through these 4. But if you then, each of these had strands, you would basically be adding more conductors, and if you're increasing the number of strands, you're kind of just taking up more space with insulation. But I don't know, sometimes it's easier to just use thinner wire as well. That's probably the only advantage. I don't know, Faustin, do you have any input on stranded wire versus a solid conductor?
Yes, the ohm values
Mm-hmm.
are different. The ohm value is different. Solid has less ohm values, but mechanically flexibility,
Yeah.
the stranded is more flexible to make the curves.
Yeah.
So you have to make a trade-off on what size is your motor, what's the
Yeah.
bending, and then of course the solid makes less heat because its resistance is less.
Yeah.
Plus, when you have high frequency currents,
Yeah.
they tend to go to the surface of the wire. So
Yeah.
when you have solid, you have less efficient space because they don't stay at the center. They go, but in the other case, you have more cross section. So all of them, I think the software will find that for you. I don't think that's you should be worried about.
Yeah. What he's talking about is like something called skin effect, where if you have this really thick round wire at a really high frequency, basically all the current is going to be concentrated in this outer region of the wire, and less current is going to be flowing in the middle of the wire. So then the cross section of your wire is basically decreasing as the frequency increases, which will then increase the resistance.
And I'm sure you know that what is the force that pushes the electrons to the surface? Hall effect. You remember that? It's a Hall effect that pushes them to go at the surface of the wire.
And also, some people use rectangular wire because that actually helps with skin effect.
And that's good because rectangular, if it's like a bar, they are flexible in one dimension. So this is good actually, and they have less waste space between the circles.
Mhm.
So I prefer this. If you can make
Yeah.
this wire, this is the best choice.
Yeah.
And they're a little bit more expensive.
All right. So I'm gonna move on to the rotor. So the number of poles is already 4, so that's fine. And then Here's the core. So I made the inner diameter of the stator 181. So I'm going to make the outer diameter 180. So there's a 1 millimeter air gap. And I'm going to make the inner diameter like 40 millimeters. And the length, I'm going to make it the same length as the stator, 200 millimeters. And the same stacking factor. And then I'm going to assign the same steel that we imported for the stator. And then here you can select the pole type. So there's these different configurations. 3, 4, and 5 are like basically the same, except there's differences in the slot for the magnets. But I'm going to use 4 because that's a pretty like common angled magnet configuration. And now we're going to set the dimensions for that. And I wish you could zoom in on this like diagram they give you, but you can't really. So it'll show you what dimensions you're actually inputting. So D1 is going to be D1, where's D1? Okay, they're not showing me. Limited diameter for magnet ducts. Okay, yeah, so D1 I think is going to be basically the magnet duct. What is the maximum diameter that can be? So if this is the edge of the rotor, this is the edge where the magnet duct can be, and then the magnets go in here. So I'm going to make the edge of the magnet duct maybe 178, so it's like 2 millimeters away from the edge. Maybe 177. And then for the magnet duct dimension, I'm going to make it, maybe I'll separate them by like 5 millimeters. And O2 is going to be what spot how far or how close it is to the center shaft. So these angled magnets, how close are the edges to the center shaft? I'm going to make that 15 millimeters. And then B1 is going to be the magnet shaft or magnet slot thickness. I'm going to make it 8 millimeters. RIB is going to be one of the slot dimensions. I'm going to just make it like 5 millimeters. And then HRIB is another one. I'm also going to make that 5 millimeters. And then layers, I'm just going to make it 1 layer. So I think that refers to how many like magnets there are in each of these holes. So I'm just going to do 1 layer. The layer pitch, there's only 1 layer, so I don't really need to do that. And then the magnet thickness, I'm just going to make it the same as the magnet slot. And then the magnet width, I'm going to make it, so if this is like 180 millimeters, or not, it's 180 in diameter. Maybe I'll make this like 150 millimeters. Maybe 120 millimeters, or I don't need to input millimeters. And then the magnet type, I'm gonna import the, what is it, N42SH material that's on canvas. Just hit OK. the shaft. It's just saying, is this made of magnetic material? And basically this is what the final result is going to look like somewhat. And I'm going to save it. And then I'm going to hit analysis and add solution step. And I'm going to say rated voltage, maybe like some sort of car. It would be like 400 or 500 volts. And I'm going to say 6,000 RPM for the rated speed at so if it's 4 poles, that should be like 200 hertz, I think. Hit OK and save that. And then I'm gonna import this to the software hub. So I'm gonna go to the software hub and open the virtual computer lab for Ansys Electronics. And then I'm gonna import the file we were just working on. And then when I go to setup, I can right click the setup I made and then click create Maxwell 2D design. And then hopefully all the parameters are fine. And then it'll basically just like build a model for you. And now it'll make a Maxwell 2D design for you. And for setup 1, I'm going to hit analyze, and it should run and create some plots in this results tab. I made, so basically this is, it doesn't tell me this is an error before, but it says the rotor and magnet 2 and the rotor and magnet 1 are intersecting, so I might need to define the geometries for those inside of the RMxprt. So the rotor and magnet 1 and magnet 2. So I'm gonna just make the thickness a little bit smaller. So I'm gonna delete this design. And I'm going to go to the pole and change the magnet thickness to like 7.5 millimeters. I'll reduce the length to like 100. Apply. Okay. And then save it. And then I'll right click the setup and then create Maxwell 2D design. Alright. Hopefully there's no geometry errors again. So now it's running, and it might take a little while, but so here's a few of the things it'll basically just set up for you. So I think it actually defined the band backwards. So I don't think so. RMxprt kind of makes errors by itself. So I think the the motion setup is wrong because the torque is looking kind of sinusoidal. So I think it's not actually rotating in the right direction. So if you make an RMxprt design, it'll make pretty good geometry for you, but you might have to input your own like motion setup and stuff like that, similar to how we did in the last lesson, basically. But
Alex,
yeah,
is it possible you redesign this but with 6-pole machine?
hmm
Keep this rotor as is, but you have 36 slots, right?
hmm
Make it 6-pole machine.
So I'm gonna go here and actually, so first I'm gonna go to the stator, and if I change the number of poles in the stator to 6, hit apply, it's gonna change the winding, I think. So yeah, so that should be fine. Now the winding pattern's different since we changed the number of poles. So we have the same number of slots, but now we have a different number of poles. So there's going to be, I think this is A, and I can't really tell, it's a little blurry. So I think this is going out, and this is going in, this is going out, this is going in, this is going out, this is going in. So now this should create, so this is going out and this is going in. There will be, the field will be pointing that way. This. So now there's 6 poles in this motor. And then the rotor, I'm going to change it to 4 poles, or 6 poles.
No, keep it as.
Keep it as 4? Okay. Yeah, you have to have the same number of stator and rotor poles, I think, for it to generate a design. So I'm gonna add, I'm gonna make it 6 rotor poles. And now you can do the Maxwell 2D design again, and basically it'll create a new geometry that has 6 poles instead. So if you want to like create the geometry for one of your projects, this is pretty useful. Basically, it's what I'm trying to show you. But sometimes it's not very good at creating the final simulation. So I'll try running this one. Yeah. Yeah, I still don't think it's set up right. Let me see.
It would be better if we could have 4 poles at the rotor. Why do you say
Because if you say the stator has 6 poles, the rotor has to have 6 poles. I'm gonna just try something. Yeah. I might teach you guys how to do the dependent and independent boundary. That's basically a way of simplifying the model to only being like a slice of the motor so that it runs faster, and you'll basically just use like a symmetry multiplier in order to multiply your result times the amount of slices the full motor is. And that's basically, usually RMxprt will simplify it using a dependent and independent boundary like this. But I think I don't think the model's set up right, basically. So if you use this, you can try to simulate it, and if your results look good, it probably set it up right. But if it didn't, you might have to basically watch the previous videos about how to set up models in Ansys. Maybe I'll make a model or I'll make a video explaining how to set up an IPM motor in Ansys to show you basically what variables you need for the different phases and all that. But for now, I think I'm just gonna end this RMxprt lesson and just have basically open office hours for the assignment that's due tonight.